All right, so let's go through a quick example of the next type of question that one could ask for buffers, which is how to use a buffer. And we'll base this on the buffer that we built in the making a buffer video, which perhaps you've already seen. So in that, we made a 200 millimolar tris HCl buffer at pH 7.5. And at 200 millimolar, we've figured out the concentration of tris base, the deprotonated version, was 0.04 molar. And the concentration of tris HCl or tris H plus, the protonated version of that buffer molecule, was 0.16 molar. And we figured that out with the Henderson-Hasselbalch equation. And again, if you haven't seen that, check out the last video. So now, within the category of how to use a buffer, we'll take this information and say, add, what should we do? We'll just add 20 millimolar of sodium hydroxide. Okay, so I'm just sort of making this up at random. And then we have to ask what the final pH is. So pH equals what? So again, let's just go through what our equilibrium looks like. So again, we have the acid, which is the conjugate acid of tris base, which we're going to call HA plus, dissociates into H plus and tris base. And this all feeds into the Henderson-Hasselbalch equation, which I'll just put here so that we can pay attention to it, plus the log of A over HA. And now I always just like to stop and ask myself, well, chemically, what is going to happen when strong base, sodium hydroxide, gets added to a buffer system? And what will happen is you get the OH from sodium hydroxide. The hydroxide itself is going to, in order for this buffer to be functional, it's going to need to be neutralized by our weak acid, which in this case is tris H plus, tris HCl. So these things will get together to make water and tris base. And so chemically what's going to happen is what we've already figured out is how much of the weak base we have and how much of the weak acid we have. And it is the acid that's going to need to react with the strong base that's added. And so really all you have to do is plug this into the Henderson-Hasselbalch equation. Now remember, we did this at 1 liter. So those concentrations in molarity are also the quantity in moles, since we have a 1 liter solution. And I didn't write moles here, that's what we're adding. All right, so if you just set this up with the Henderson-Hasselbalch equation, pH equals, now our pKa stays the same. Again, we know it's 8.1 from the last video. That is a constant which you'd be given. And that's going to equal to the log of the A over the HA. And now that'll be a different quantity now that some chemistry has happened as a result of this addition of strong base. So the A originally was 0.04 moles, and the HA originally was 0.16 moles. Now we've said that when we add hydroxide, it is going to be neutralized by the weak acid that's in the solution, or the HA plus. And so it is that quantity of 0.02 moles or 20 millimoles that will be reacting with that acid and thereby decreasing 0.02 the quantity of weak acid that we have in solution. And when we react hydroxide with weak acid, not only do we make water, but we yield that conjugate base, or the tris base in this case. And so whatever we subtract from the denominator of the Henderson-Hasselbalch equation in a use the buffer paradigm, we have to add it to the other side. So we are now adding that same quantity, 20 millimoles. Now again, I'll make the point that when we're using buffers by adding a strong base or adding a strong acid, we are not fundamentally changing the number of moles of our buffer molecule tris. All we're doing is changing its protonation state. So by adding a strong base to a solution that has a weak acid and a weak base, all we're doing is we're converting some of that weak acid to a weak base. And we could go the other way. We could have added a small quantity of strong acid to this solution, which would convert the weak base to the weak acid, and we would just flip the signs here. So again, if we just go through the workflow, it's still pH equals 8.1 plus log of 0.06 and 0.14. And those still add up to 1.2. And so you calculate that ratio and take the log. So we'll do that in our calculator. So it was 0.06 divided by 0.14, right? Right. Okay, and so that is our new A to HA ratio, 0.4285 and change. And then we can take the log of each side, and that is what we will then add to our pK value. So add 8.1. So we're just doing all this in basically one step. And so our new pH will be 7.732 and change, which will round off to the same 2 sig figs the answer was given in, which will be 7.7. So the final pH equals 7.7. Okay, so you just have to make sure, we did a couple of wrinkles of this in lecture when we dealt with polyprotic acids, for instance, that we added more strong base than we had weak acid to neutralize it, or more strong acid than we had weak base to neutralize it. Those are more complicated problems, which if anyone has any questions, feel free to knock on my office door. But I just sort of wanted to give you an example of the standard workflow of how to use a buffer. And again, how to make a buffer, how to use a buffer are very often in exams asked as part A and part B of the same question. So once you figure it out, based on the pK value and the concentration of the acid, the weak acid and weak base you're given, you can figure out your A and HA quantities. And then really the whole key is knowing how to set it up here, knowing that if you're adding a strong base, that's going to neutralize the weak acid and give you that same quantity of A. Now the other thing to remember is that we've built into this math the assumption that neutralization happens quantitatively, and that the equilibrium, basically is independent of, or the final concentrations of A and HA haven't changed. And so when we do this neutralization, is it technically at equilibrium? No, but because our A to HA ratio is still between 0.1 and 10, and we still calculate a pH that's within 1 pH unit of the pK value, it's still a valid buffer. And so we were able to use the shortcut where we could just add the amount of base added to the numerator and subtract the amount of base added from the denominator, representing this chemistry we've shown here to calculate our final pH. So if you have any questions on this or similar problems, let me know.